Welcome everyone and thank you for joining us. My name is Steve Case. I'm with the marketing department here at Electro Rent, and thank you for joining us on our webinar, which is for Fronthaul Network Evolution, Building a Robust 5G Network. Our presenter today is Eduardo Anunza. He's an RF Test Global Market Development Manager for Viavi with over 25 years of experience. And with that, Eduardo, I think we're going to pass it over to you. Let's get started.
Thank you, Steve, and hello, everyone. So in this session, I'm going to be talking about Fronthaul and how we have seen Fronthaul evolve. And not only, I'm going to briefly be talking about on the concept of different technologies around Fronthaul, not only on the physical layer, but also on what I call the data layer. And also going to be talking about some of the use cases that we have seen as it relates to the deployments of 5G. So that also is going to involve 5G in the low bands as well as 5G in the millimeter wave. So I'm going to start with just an overview of the Fronthaul. And so first, basically, we have, let me call it the semi-traditional Fronthaul, where from left to right, we have the gateways, 4G, 5G gateways going into the backhaul transporter over Ethernet, reaching a baseband unit, and then from the baseband unit to the remote radio head. And this is basically traditionally being called the Fronthaul, which is being carried over this protocol called CPRI. I'm going to briefly describe what CPRI is and the benefits of CPRI, but this is basically what we have seen traditionally in LTE. Now, as it happens to be related somewhat with 5G, this is basically what we have seen deployments on perhaps the new band, CBRS band, although this band, CBRS, is truly a mid-band. It's a 3.5 gig, but nevertheless, same radios being used, the same topology is being used for its deployment. And I think more on the 5G world, we probably have seen DSS, or dynamic spectrum sharing. So basically, this is the notion of transmitting 5G in conjunction with the LTE channel. So just to keep it simple, they are basically mixing time slots between LTE and 5G. So I'm making all those reference just because, as you can see, the usage of the Fronthaul, even for 5G as well on those cases. Now, the other case for 5G is in millimeter wave. So here I have as an example on the radio axis, we have radios that are transmitting in millimeter wave. Millimeter wave, or frequency range 2, is basically up in the 24 gigahertz or higher. We've seen typically the 28 gig band and the 39 gig band. Now, for that, basically the FCC provided a lot of frequency available. So that demands a lot of bandwidth. They can carry or transmit over close to 1 gigahertz of bandwidth on the spectrum. And as you can imagine, just to make a quick comparison in terms of bandwidth, here up in the LTE world, the carrier bandwidth was up to 20 meg. Here in the millimeter wave, it's 100. Actually, it can be higher than that, but typically we have seen deployments of multiple 100 megahertz. That bandwidth certainly is changing the Fronthaul. So in the past, here the Fronthaul was managing all those different branches in LTE. Now when we go into 5G with high capacity, which is in millimeter wave, certainly will require a different type of Fronthaul. So we have seen a mix in the early deployments of these radios of multiple super links, as well as the introduction of the notion of an evolved CPRI. This concept on the new protocol is basically being defined by an open radio access network group, or the ORAN group, with which, in addition to cover or tackle the problem or the challenge of bandwidth, also, even perhaps more importantly, they decided of, hey, at the same time, because of all the requirements that we have to build on 5G, as well as the ability to have multiple elements and provide the ability for people to interact with different network elements. Specifically, if I want to have here as my, instead of my baseband unit, is going to be a centralized unit and a distribution unit, and these can be just software. I can have these virtualized just to have different appliances, so I'm not going to have a dedicated servers. And also here in the radio, I can have a different radio flavors. So that gives a lot of flexibility to mobile operators on its deployment. So because of all those reasons, the Fronthaul is now changing into this concept defined by ORAN. At the end of the day, basically here the goal is to have a Fronthaul actually some sort of partitioned into two pieces. Now we're going to see a mid-haul, which basically, as you can see, if in the beginning, the centralized unit and distribution unit was on the same location, on the same site, if you will, that can be basically put it on different sites, again, to provide more flexibility. And here is basically mid-haul, everything it's in reality Ethernet. And in the Fronthaul, we're going to have a mix. Typically, what we have seen is that here on the cell site, they collocate radios. So is going to be typical to see, for example, now with the C-band, that we're going to have LTE in one area or in one layer of the site, collocated with C-band radios that are going to be on the same site but different antennas or different radios. And also we might have millimeter wave. So as you can imagine, on the same site, we are going to have different radio components and radio pieces covering different bands. So at the end here, we might have a mix of different Fronthauls. But at the end, again, basically we're going to be seeing what it currently exists on CPRI and what is going to be coming up in the ORAN defined as eCPRI. So I'm going to first cover the physical layer aspect, which is a little bit more simple. And then I'm going to be talking about a little bit more on the protocol, which is on the data layer. So some of the things that we have seen in terms of the physical layer. And again, I probably put a little too much information in this slide, but I just want to give you a representation of what we are saying on the physical layer. Physical layer, everything is going to be fiber-based. So here we have different fiber links. I'm just showing here some rings here on fiber, which basically, as you can see, they have in different colors, meaning that they have different wavelengths traveling on that fiber. So if in the past, as an example, on a CRAN concept, actually, let's kind of be thinking about this section here on the left as a CRAN, as a centralized radio access network. I have here, I don't know, in San Francisco, a cell site in a building, and just shooting different fibers that carry a single wavelength into all those radios. These radios are basically deployed in the rooftop. So that is basically a CRAN piece with, again, a single wavelength fiber. I can cover that traffic. However, there's going to be other type of radio elements, as the example that I mentioned before with millimeter wave here in a very dense network. So same example in San Francisco. Here, perhaps instead of having just a few of these sites, I'm going to have many more of these millimeter wave radios. And because of its capacity that it's needed, I need to provide them with multiple wavelengths going up into each of those radios. And one of the other aspects that why it is required more density and not just using the same radios and just collocating the millimeter wave radios. That is because in millimeter wave, on those high frequencies, we don't have the same coverage. It's significantly less coverage that we can achieve on higher frequencies. Therefore, we need to deploy more of these high band radios than we traditionally have done here on the low bands. In any case, so that's the reason why we're seeing a lot of more density of these type of radios. And just going back again into the physical layer, the connectivity that we're going to see back into the network, it's going to be using multiple wavelengths. So we are seeing that even if in the past we saw a lot of wavelengths here on the core of the network, now we're seeing those being in the axis of the network. Okay, so this is basically, again, here I just put a different mixes of 4G and 5G radios, and how not only fiber is going to be more prevalent, but also how more wavelengths are going to be needed. So the technology being used for that ability to deploy different wavelengths on the same fiber, single fiber, different frequencies, if you will, or different wavelengths, is with this notion of division multiplexing. So here we have, this is just a simple chart that I have in terms of the properties of frequencies for fiber or optics, and how much the attenuation affects through the different frequency bands in optics. So first we have just a wideband wavelength division. So we have two main channels that were used. So again, just two different sections, so doubling capacity, if you will, from a single wavelength. That evolved into the coarse wavelength division multiple access, and actually we have seen a lot of deployments using this technology, DWDM. And as you can see, we have now many more channels, all the way up to 18 channels that can be used for fiber transmission. So certainly a benefit. However, the technology that we have seen more promising is DWDM, so dense wavelength division multiplexing, because now all of a sudden on a single band here in C-band, as you can see, now we can transmit 96 different channels or wavelengths. So certainly we're multiplying significantly the capacity of that fiber. And this is the technology that we're seeing being deployed most of the times with DWDM. So before I go further into, again, just trying to cover some of the concept of a physical layer, and then I'm going to be briefly talking about the data layer. I'm just going to pause for a second to see if we have any questions.
Yes, we do. So we have two questions. The first one is, how is eCPRI different from open Fronthaul that's used in ORAN?
Oh, okay. I'm going to explain that on the data layer, but you can view that is basically the same. eCPRI is part of ORAN, and even though the CPRI organization defined eCPRI is basically being used by ORAN.
Okay. Second question here is, what is the max distance allowed in 5G between cell site to mid-haul and backhaul?
Yeah, so that distance depends on different aspects. One aspect is the latency that you might have, and this is also kind of becomes the concept of where all the signal processing is going to take place. So if now with the edge computing happening, then the distance can be greater. Previously, we've seen some limitations in terms of distance on CPRI, and that is because with CPRI, basically all the signal processing was happening or was handled by the BBU. And if we have, for example, that topology that I mentioned CRAN with a bank or a hotel of BBUs, there were certain restrictions of distance because it was just basically a constant bit rate transmission over CPRI, and therefore there was a delay problem or latency problem, and right. Therefore a limitation on distance. The distance at that time, it was about, I don't know, 6 miles or so. Now with eCPRI and changing that model into a different packaging, or they call it functional splits on the data, that distance can be much greater because, again, all the signal processing has been fragmented into different components, into the central unit and the distribution unit, and also the transport mechanism also changed. So now we have more flexibility.
Okay, we also have a related question just come in. Can we use the same BBU in CRAN like we can in DRAN, or does it have to be upgraded?
No, it can be the same. The same baseband unit that you can have just at the base of a macro cell can be the same that you can remotely put it on a central office or as I call it, a hotel BBU, and just extend the fiber. The fiber connection that goes from baseband unit to the remote radio head, you can be just extended, but it can be used the same baseband unit.
Let's see, we have another question. Let's just try to do it. Is eCPRI completely open, or is there some proprietary functions like in CPRI?
Yeah, so still, as of today, there are some vendor-specific functions, and there's a lot of different variables that ORAN wants or needs to tackle just to have a fully interoperability between different network element manufacturers. Currently, still, it hasn't been totally defined. I think ORAN has been covered some of the basics, but we haven't yet gotten into a point in which it's fully open. But let me put it this way: the group is working towards having it totally open and have, as I said, multiple elements being able to connect between themselves.
Right. At this point, Eduardo, I think you could continue, and then we'll take another break, and we'll kind of pause the questions at this point. Go ahead.
Sure. Okay, so data layer. So I'm going to probably spend a little bit more time here on the data layer because this relates to the protocol. So I'm going to start with just basically what we've seen as of today in terms of baseband units, connecting fibers into the remote radio heads using CPRI protocol, the CPRI interface. As I mentioned before, here with CPRI, we can transmit not only LTE, but also 5G in the sense of using it with even, as of today, we probably have seen 5G radios being deployed in the 600 megahertz, or even radios in the 2.5 gigahertz. Basically, they were using CPRI as their interface. Even now with other type of technologies that we have seen 5G being deployed, like, as I mentioned, DSS, dynamic spectrum sharing, that I think we have seen that a lot of mobile operators have embraced that technology because they can use their existing sites, the existing LTE sites, basically with just a software upgrade into the radios to transmit also 5G 5G signals, and that's been done basically by sharing that channel. So again, the Fronthaul hasn't or didn't change on that model, but we'll see that, as I mentioned, that's going to change by putting or fragmenting these signal processing into different elements, and just having the radio here a little bit more, I don't want to say less smart than what it used to be, but having it in a way that it's truly going to be open. And the connectivity here, it's going to be with eCPRI, and between these two elements, the central and distribution units, we're going to have another mid-haul connectivity that is based on Ethernet, although it's been defined as the F1 interface. And these elements actually were defined, as I mentioned, as a functional split. So ORAN kind of looked into it, and they basically said, okay, so there are different functions, and again, I simply put it as signal processing. And that signal processing, they put different blocks to describe what type of processing that's going to be done. So as you can see, they have different options on where these split will happen. And they decided, or the industry decided, to embrace, okay, these connection, this connectivity, and this whole signal processing that we're going to have here in terms of the radio link control and the media access control is going to be part of this distribution unit. So here, the F1, it's going to be this link between these blocks that are going to be part of the DU to these other blocks, which are going to be part of the central unit. This is one piece. The other piece now is what is called the low layer split. This is where the eCPRI resides, where say, okay, so now we have the low-fi and the RF here in the radio unit, and all these other pieces are going to be part of the DU. Just as a reference, even lower here, I have the RF piece. This is where the CPRI interface used to exist, or used to be. It was just between the RF or the radio and back into the baseband unit. But as a reference, I just included there as a functional split. And what we're seeing currently with ORAN, it's these two main splits, the high layer and the low layer, and that's how basically they define these front haul and mid haul connections. But so what is CPRI? So I'm gonna just briefly describe what CPRI is, and then I'm gonna try to do the same on eCPRI. So CPRI as a front haul basically was defined, okay, so I'm gonna have a connectivity between the BBU, the standard call it radio equipment control, and the remote radio head or remote radio unit, or what the standard called radio equipment. So it was going to be this interface that generally there are going to be three main user planes that they need to be aligned between these two elements. One is the control and management plane, basically the ability to start communication, to sending some data out, and the receiver will understand what kind of information is coming. Then it's going to be the synchronization plane. On sync plane, basically just to have a proper timing between them. And this was very, very easily done because, as we will see, this connectivity is an always connected transmission. So it's always connected. So basically here we have a constant bit rate happening. And then the last piece is the user plane. User plane, view it as just all the data being transmitted for uplink and downlink on the radio, so the actual traffic that is happening. So that is basically just in very simple terms, the basic concept of CPRI. The key elements of CPRI, however, I want to highlight because it might be different, or it's going to be different than eCPRI, is that with CPRI, we have a constant bit rate transport. So again, this connectivity is always connected, is not packetized, and we will see that it is CPRI where you can have different packets, and it's a non-always connected mechanism, whereas here is constant bit rate. The other piece is the speeds that here in CPRI I can use. So we have rate 1 at 614 all the way up to 24 gig, which is rate 10. Why is important? It is important because depending on how fast I can transmit is the bandwidth that can be allocated into this pipe or into this link. So for anything in terms of low and mid bands that basically has some sort of limitation in terms of bandwidth, even as I mentioned, LTE, we can transmit 20 megahertz worth of data on a channel. Now we can have multiple branches or in multiple input, multiple output, or MIMO. Basically, you have multiple of those channels being transmitted all the way up to 8. And then if we have some multiple carriers that can be aggregated, that basically it's what LTE Advanced allowed, then as you can see, the bandwidth is basically growing and growing, not only because of the bandwidth of the channel itself, but also because we have MIMO involved, so multiple streams coming in or being transmitted out, as well as the ability to aggregate channels. And by that aggregation, it can be in the same band or in multiple bands. So even you can see that here in CPRI, here we have one remote radio head, but basically I can daisy chain another remote radio head, and on the same CPRI link here on this one, it can be transmitting the signal of one radio and the other radio if I have that daisy chain or that cascaded topology of multiple radios. So as you can see, that is how just bandwidth got a lot of growth. Therefore, the CPRI community defined this bandwidth to be all the way up to 24 gigahertz. Now, the other aspect that I briefly mentioned is the ability to have a mix of radio access technologies. And the example that I gave on cascading radios, we can have a radio that is, let's say, in, I don't know, 700 megahertz band, and then I can cascade another radio that is in the 2100. So again, that is possible. Each one of them might be having carriers of different bandwidths. So 700 might be, or yeah, 700 might be in 10 megahertz carriers, MIMO 4. The next radio that is cascaded in 21 can be 20 megahertz channels in MIMO 4X. So in any case, all those packets, those are called antenna containers. So all those antenna containers with mixed technologies can be transported on a single CPRI connection. So that was certainly possible. And the other aspect that I want to tackle or to mention is the proper time and synchronization. In essence, it's just from a timing perspective, typically there's a terminology of master and slave. Master or a primary reference clock being derived by either cesium or GPS. Typically that is how on central office all these network elements get synchronization. So typically a baseband unit has a synchronization port, and the radios, they just behave as slaves. So basically they get sync from CPRI, and again, since it's a constant bitrate transport, that was done easily. So now just a little bit more on CPRI, how basically that works. I'm going to start from an analog signal. So we have here in RF, we have a signal coming in, and basically CPRI allows us to do sampling of that signal. And then we have different sampling of the data. We can have stuffing bits in between. Therefore, we can actually go and group those signals. We'll first map the signals into these antenna containers. So again, this can be a 5 megahertz, this can be another 5 megahertz. If I have a 10 megahertz signal, so I can group them. So with these groups, I have here a 10 meg or a 20 meg or 15 meg signal. And then that is just being put up into just basic frames and transmit those constantly. And again, just highlight again the different line rates that we can use CPRI for. Typically, we have seen 2.5 gig and more recently 9.8 gig. The standard, however, allows us to go all the way up to 24 gig. And yet again, this is an always connected type of protocol, and we are getting just a constant bit rate. So some of the usage that we have seen, not only in terms of the connectivity between the remote radio head and the baseband unit, it's also the ability to do some testing here, not only on the CPRI protocol itself, what I call the CPRI verification, but also the ability to have an optical splitter and have basically a sample of the data being transmitted by the remote radio head down to the baseband unit. So in essence, we're going to be able to have the same visibility of the RF signal coming in by just demapping all those RF components. And basically here, following the CPRI protocol, now we have visibility of the RF. And why that is important? That is important because if we have interference problems, not only external interference, but also passive intermodulation, that basically limits the use of the channel by just if you have a lot of noise coming up. Certainly we have a lot of UEs being competing with that noise, or even might be happening that the band is not usable in some number of resource blocks. So certainly important to have that visibility. So for that visibility, we have the technology called RF over CPRI, and as you can see here in these a couple of examples, we have visibility of the signal. In this example, in the middle, I'm showing just a MIMO 4X. So we have same channel but 4 different data streams, and then we can certainly test each of those channels through time for an analysis of intermittent interferences. So that's a practical aspect that certainly a lot of mobile operators are now using in terms of just CPRI. Now, we're going to talk about ORAN. So on the Open Radio Access Network, we've basically have seen that they have defined all these different aspects on the right-hand side, and I'm not going to go through all of them, but I just want to pick what is the open Fronthaul, and is this section down below. But in essence, the industry, it was actually the ORAN group started back in 2018 by different mobile operators, and again, their objective was to have the ability to define all these different functions so it can simplify the operation, and we can use different components or different devices, if you will, not dedicated pieces of hardware, to deploy the network to make it more intelligent. So the ability to have it open, virtualize, and interoperate with different vendors. Now, inside of the ORAN group, we have different work groups, and the work group that is being concentrated on this open Fronthaul is the work group 4, which actually we participate on that work group. Now, let me just explain a little bit more about that open Fronthaul, and I'm going to just look into a functional overview. First, the management plane. Again, this is just the ability to have these 2 elements been talking, basically sending, hey, can you hear me? Say, yep, I can hear you. And just saying, okay, so what type of radio you are, what kind of antennas you have, a power level that you have configured, all those kind of simple aspects. The other layer or the other plane is the synchronization plane. Now, as we can see, the ODU is going to be working as the master, and the RU is the slave. Now, since these connectivity in the eCPRI, it's based on Ethernet. Now we're not going to be able to have an always connected type of connection. Now it's packetized. So we're going to see now a new way to deliver timing is being defined by PTP, or Precision Time Protocol 1588. So that's basically how now sync is going to change. And then we have the user plane. So user plane again, just okay. Now that we're talking and we are in sync, now I'm going to be sending you traffic. So I can open up the IQ data for downlink and uplink, so we can establish some calls. And then finally we have the control plane. So just to have full beamforming and full signal processing coming up. So these are the 4 main planes defined in ORAN. Okay, so now again, I'm gonna take just a simplistic view on ORAN eCPRI and different cases that we have seen. So yet again, here we might see a case where we have the central unit, the Ethernet mid-haul into the distribution unit, Fronthaul eCPRI, which actually it's over an Ethernet transport into my radio unit, and then we have coax cables down here into my antennas. So that's one topology. A different topology, perhaps it's going to be that these 2 pieces are not 2 different components, but it's just a single radio. Basically, we have an integrated radio unit with an antenna. Typically, this is what we have seen in millimeter wave. In millimeter wave, we're seeing just a single element. So this connectivity of coax doesn't exist. Typically, we've seen this coax connection on macro cells. In the small cells, it's just everything integrated. And we expect that to be also the case for the C-band radios. Now, the other use case that is a little bit more complex, but I think it makes a lot of sense, is to have in between a network that it's based on DWDM. So we can have connectivity to multiple radios. And as you can see here, we have another elements, the Fronthaul transport nodes, or there is some other terminology being used for the same purpose as Ethernet Fronthaul muxes. But in any case, the goal of these elements is basically to get all the traffic transported over into a DWDM, and here at the end also have the ability to support both the conventional LTE CPRI protocol and also the eCPRI protocol. So it serves a couple of objectives. One is not only to transport over into a DWDM network, but also to have a hybrid traffic and serve the existing LTE and the upcoming 5G. Okay, so I'm going to be now touching some aspects on how we can test or verify the Fronthaul. But before that, I'm going to pause and see if we have any questions.
Yeah, we do. We have one question, and pretty good. So can all of the use cases, such as the enhanced mobile broadband and ultra-reliable low-latency communications and MMTC, be realized in the 2.5 gigahertz part of the spectrum?
I will say it's a tricky question, because in 2.5, I'm going to revert back into this slide. The ability to have the ultra broadband connectivity for mobility, that typically is related to the ability to have a lot of bandwidth on the RF. And in 2.5 gig, that's just a band, but it all depends how much bandwidth or how much frequency a mobile operator has. So if in 2.5 gig, or even now with C-band on 3.7 gig, it all depends on how much bandwidth they have to provide that bandwidth into mobility services. So if in 2.5, as an example, we only have, say, 20 megahertz, then that ultra broadband aspect of 5G will not be able to achieve. If we have higher bandwidth, then it will be possible. And by higher bandwidth, I meant to be at least 100 megahertz. And that is basically what we have seen now with the C-band. And the C-band some mobile operators, they have that capacity to transmit 100 meg or more, and that is basically can be referred as ultra broadband probability. Now, in terms of latency, it all depends on the how rapid the network is going to respond to applications or services, and that is basically driven by the edge computing concept that I mentioned before. So the signal processing, where is it going to happen? If it's going to happen close here to the radio, or if all the signal processing is back into the core. If it's back into the core, then as you can imagine, we're going to have a lot of latency because the signal needs to travel all the way up, do its processing, and travel back into the radio. Now, if some of that signal processing is being distributed and is being now closer to the radio, then we might be able to have a low latency, therefore high response in terms of services. So yeah, it all depends on how the network is built.
Okay, very good. That was the only question, Eduardo.
Okay.
Oh, wait,
okay.
we have another one. I'm sorry.
Okay.
Let's try to get this one. What is the difference between ORAN Fronthaul and NGFI1? I'm not sure about that one myself.
NGF, no, sorry, I don't know the answers to that one.
Okay. All right, carry on.
Okay, so in terms of testing, so a couple of aspects as well. One is I'm going to relate back to the physical aspect or physical layer aspect of testing, which typically happens during installation, and then the data aspect, which happens during the integration and maintenance of the radio access. So I'm going to start with the physical layer aspect, and I have here some use cases, but in general, for the installation stage of basically any type of radio, macro cell, micro or small cell, or even in a DAS system, we have different elements, different components. So we can have the radio to the antenna, which might be a coax cabling, the BBU to the radio, which might be fiber. And in this case, in fiber, we can have certainly all the aspect about checking all the connectors. So that's being referred as fiber inspection, just to make sure that all those are clean, and that it's key because, well, if we have any problem with dirt on the core of the fiber, then we're going to have a lot of loss in terms of power. The other aspect is to test the fiber itself, and by that we use OTDR just to have a sense on how much attenuation that fiber is exhibiting. And then if we have DWDM, so transmitting multiple wavelengths, we need to check all the different channels or wavelengths. So we have a channel checker. And then the other aspects are related to the antennas themselves and how the antennas are aligned or must be aligned. And then at the end of the day, truly, even though you can see that it's all bit tedious or multiple tests, all of them can be fully automated. So that's basically what I'm referring here as test process automation. We can basically, and just to keep it simple and brief, we can have all different MOPs or test criteria for cell sites being digitized and being pushed into the test sets, into the test instrument. So in essence, we have a single test instrument that can handle all these different type of tests during an installation of a cell site. So let me go and give you some examples. In terms of testing, again, first is the inspection, looking into all the connectors, providing fiber characterization, if you will, or fiber verification with an OTDR or channel checker, testing coax and macro cells, and then antenna alignment, and all of it basically being automated, and having, again, not only the ability to push all the test requirements for all these different aspects, but collect all the data and basically put it into the cloud. So again, just even though kind of being looked as different multiple test everything can be simplified. So the first example that I have here is in a macro cell. So in a macro cell, again, looking into a DWDM going into a baseband unit, a single fiber here coming up on Fronthaul into a 4G, 5G macro cell. So basically we look into it. This is roughly how a baseband unit looks like. So here we have a BBU, and here we have the 3 sectors, fibers going into each of those sectors. So we have here on top 3 sectors, each one of them with a pair of fibers. So that's why here I'm just pointing out on this baseband unit that we have radio 1 sector alpha, beta, and gamma, each one of them with a fiber. So all of it certainly needs to be verified and tested, not only in inspection, but in point-to-point. And this is basically simplistic, perhaps not all the times, or rarely. You might have here an LTDR trace. Typically happens when you have a longer type of fiber. So in a CRAN type of environment, yeah, you might want to do an LTDR. Here, when you have a point-to-point as short distance, is not much being used as an LTDR type of testing. The other test, so here we have a macro cell. Yeah, certainly you need to align the antennas, and you have a coax cable running from the remote radio head into all the antennas. So here, as you can see, I'm just pointing out the different elements. We have the remote radio heads being installed, the fiber that is coming from the baseband unit, and the coax that goes from the radio to all the antennas. And as I mentioned, just everything can be fully automated, and a quick report can be generated. Second case, with a macro cell, but now with FR2 or frequency range 2, that means we have now a millimeter wave radio. So in this case, we have DWDM into the mix. And here we have a DWDM ring actually going in here on the MUX, DMUX DWDM. As you can see, the ring is coming in and out. And as a drop, here we have the specific fan out fibers. So similarly here now we have a 5G radio, fiber 1, 2, and here we have a second radio, fiber 1. And here on top, we have basically the other fiber of my 5G and a couple of LTE on different bands. So again, this is just an example on how with DWDM now we can associate or assign different fibers for that purpose of different bands and different technologies. So here as an example on the alignment, we have a 4G radios up here, and collocated we have the 5G radios, as you can see, much smaller, just because that physically that can be achieved by higher frequency millimeter wave. The antennas are significantly smaller than on 4G. And then the last example that I have is just a dedicated frequency range 2 small cell. So again, millimeter wave. So now here we see that actually these MUX is at the base of the site. Here we have a dropout MUX. And then here, since we have basically this is a small cell, as you can see, the cell is pretty small, and we have connectivity to all these different sectors. Here the goal is now that these radios are high capacity, we need to check that on a single fiber that is coming in, that all the channels or all the wavelengths are properly equipped to transmit all these traffic for the radios. So these are kind of just the use cases that we have seen. Now I'm going to be talking about the other aspect that is not the physical, but it's only more on the data or the protocol. So here in the protocol, we have the ability to basically test for the transport. So here I'm now shifting into the ORAN concept. So the ability to test the transport and the synchronization aspect of it. So in between the distribution unit and the radio unit, certainly we can have that transport testing mechanism. And we're going to be able to check not only for power and frequency offsets that we might have, but also the packets that are being exchanged between the DU and the RU. And also, as you probably remember, in terms of synchronization, since this is a packet type of interface, then the synchronization is going to be delivered via this PTP or precision time protocol concept. So certainly we also have the ability to test for the PTP connectivity. So now going beyond that, beyond just that the transport layer, now in terms of the user planes and control planes that I mentioned before on the stack of ORAN, certainly we can also perform that type of testing. So we connect similarly a splitter between the distribution unit and the ready unit. So we're going to be able to have the ability to monitor the exchange data that happens, and then not only to verify the control and user plane, but also for troubleshooting purposes, we're going to be able to basically capture data and even filter data and present data. So there's going to be the ability to test that truly. Let me give you an example. If we have a distribution unit for NEM1, for a network element manufacturer 1, and we want to connect that into a ready unit from a different vendor, we can do so by making sure that not only they are talking to each other, but they understand what each of them are talking about. So that understanding aspect, it's basically related to the control plane and user plane verification. And then in this aspect, or in this diagram, I'm just showing the similar concept that I mentioned before, the ability to have these Fronthaul transport nodes that with which we can combine the CPRI links and the eCPRI links and put it over into a network. And then at the end, I'm going to basically have it down into the same CPRI and eCPRI and transmit that over. So even a little bit related to the question that had been asked about latency, we also can have testing on all the FTN and how much latency this network might have, and not only the network, but all the different elements. So these Fronthaul elements might have some sort of delay for processing going into the network, also some sort of delay in processing of the Ethernet Fronthaul here as well. So all that we can test not only for the latency itself, but if it exists any packet delay variation or any jitter. So again, just the ability to make certain that the whole pipe is going to work properly for eCPRI as well as CPRI. And then in terms of synchronization, here I just put a few more Fronthaul transport nodes. And here's the notion is basically, as I mentioned before, here the distribution unit may be getting, well, it's going to be the master for synchronization, is getting timing from a primary clock. Typically, these primary clocks derive its, or they get its timing from GPS. And basically provide that timing to the distribution unit. Here they have inside of them what they call the grandmaster. And this is a terminology being used by the PTP standard. So in precision time protocol, you have the grandmaster, and then you have down below, here you have boundary clocks that reside on each of the Fronthaul. And then at the end, the receiver, this is going to be the slave clock on the ready unit. So again, since everything is being packetized, there's certainly a level of concern that there's going to be a drift of these radios. Now, why that is important? It is important because not only latency and the response that the network is going to have into the UEs, but also if we have a drift of one of these radios that is different from an adjacent radio, the call is going to drop. So certainly mobile operators, they want to avoid that at all costs. So there's very distinctive criteria to test for timing. And certainly we can do so. We have the ability to connect or have the same primary reference clock derived from GPS. And down here, we can actually make the test against GPS to see how much of drift basically exhibit or delay exhibit these all these elements. And with that, want to thank you all. Just want to cover again briefly some of the physical and data aspects and a quick overview of how CPRI and eCPRI work and some of the verification needed again on both aspects while installing on the physical layer and also when you're integrating or maintaining the radios in eCPRI. Do we have any questions?
No, there are no questions. So what I'd like to do is thank you, Eduardo. This was a fantastic presentation. We do have copy of the webinar in the handout section, and then we have another handout, also the test guide to 5G from Viavi. Thank you very much for that, Eduardo. And we can take questions right now, but I did want to mention that those handouts are available to everyone. Then take those before you we finish up here. And I don't see any more questions coming in, so we'll wait here a couple of minutes to see if couple seconds here to see if there are any more questions. No questions are coming in, so I'd like to thank everyone today for attending the webinar. And Eduardo, thank you very much for giving us all this detail. It was fantastic.
Thank you all. Thank you all for the time. And yeah, feel free if you have any questions later on, feel free to reach out. But thank you for attending.
All right, thanks everyone.